Hi everyone, I'm back with another Leetcode problem. Today's problem is problem 2519. Count the number of k big indices. So what is k big indices? Let's go to the problem description. So we're given a zero index array. Okay, so we're given an array and a positive integer k. These two things are given. Inside that array, any index I is called k big index if the following conditions are satisfied. So there are two conditions we can see. Okay, so if there exist at least k different indices idx1 such that idx1 is less than I and the value at that idx1 is less than the value of index I, less than the value of the array in index I. And also there exist at least k different indices idx2 such that idx2 is greater than I, that means the index is greater. Also, the value at that index is also greater than the value is smaller than the value at the index. So, okay. So here, if this is an array, right? So if there are like something here, something say at index I, the value is say something like array I or something like that, right? So this is called a k big index. This index is k big if there are like at least say k elements here that are smaller. So these elements are smaller than AI. So say we have here anything like B, C, D, three values, right? All of them are like smaller than AI. And as you can see, everything has also the index of them are smaller than I, right? And then we have say XYZ here. So the XYZ is also smaller than the value at index I. And obviously the indices of X, Y, and Z are larger than index I. So then we call this, here the value of k is 3, right? So we will call this 3 big. Okay, so let's look at the example. So this is our given array and the value of k is 2. We have to find out how many k big indices are there. Okay, so let's say for this one, like 3, right? Index is, what is the index? The index is 1, and the value is 3. Now, do we have like two values that have smaller index than 1, which also have smaller values than 3? No, right? There is no chance because there is only one element there. Okay, so how many we have? We have like 2. We have 2 of them. One of them is 6. 6 has an index. Let's say the index here for 6, the index is 2, 3, 4, 5. Okay, we have 5 indices. For this value, you see the index is 2 and the value is 6. We have like 2 of the elements which not only have smaller values, also smaller indices. Okay, so 2 here, and also there is another 2 which have larger indices but is still smaller values, right? So that means this is a k big index. The same thing goes for this one you see here for 5, right? So on the left side, we can say on the left side there are like 2 of the values is smaller. On the right side, there are 2 of the values also smaller. Okay, so basically any index is a k big index if on its left side there are like at least k values which are smaller, and also in the right side there are at least k values that are larger. So the definition is clear. For the second example, let's see. The value of k is 3. Now the number of, you see that the length of the array is like 3 already, right? There is no chance that I will have 3 on my left and 3 on my right. Not only that, all the values are same, right? So there is no chance that I will have smaller values either on my right or left. So obviously the output is 0. So how do we solve this? Let's say we have an array of, say this is index I and the value is say AI. On the left side, we have to have say like at least k values which are smaller, and on the right side also we have to find at least k values which are larger. So why don't we just go and ask, like, on the left side, hey, are there k values smaller than AI, right? If yes, say yes, we just then go to the right side. We go to the right side and ask the same question, like k values is smaller than AI. If both of them are yes, then I is k big, right? Okay, and we have to count. So we just increase the answer value to 1, increase the answer value by 1, right? Okay, so we can keep on doing this for how many? We can keep on doing this for each of the indices, right? Each of the indices. So in total, we have to check from 0 to n index n minus 1. That means we have to check n indices. And each time we have to check n indices. And each time you see that we are checking both the left and the right. That means each time we are checking n minus 1 comparisons, right? So this is the simplest way to do it. So on the left, I will check something, and on the right, so in total, I will check n minus 1 values each of, and then I will count if they have enough number of values that are smaller than the value at the current index. So this is order of n square algorithm. So we talked about the naive one. Now let's think how we can actually do it more efficiently. Can we do it more efficiently? Yes. So we know that we have to find k smaller values on both on left and right. So why don't we do this? Let's say, okay, for the ease, let's say these values a or something. Okay. Okay. And then, or let's make it x. What if we keep a maxip of size k? We know what maxip does. Maxip does is on its tip, it will have the max value. That means everything here will be smaller, right? Everything here will be smaller inside. Everything inside will be smaller than the top of the hip. That means max hip, we can use a max hip to store the smaller values. And then every time, so this is different array values, right? Okay, so every time we read, at the same time, what you can do is we can just keep on inserting into the max heap. So we read from here, we read one element at a time, and then we keep in the max heap. Let's say we keep on doing this, and then we reach the index I. Now, if we see, say, now the size of the heap is going to be, say, k, right? We are keeping the size of the heap k. Now, let's say the top of the heap is now is any value, say, b, right? So if b is smaller than x, right? If b is smaller than x, can we say, does it imply that everything in the heap is smaller than x? Can we say that? And how many things are there? Like k items, or like all k items in the heap, in the max heap, are smaller than x. We can obviously say that, right? Yes. Yes, we can say that. Now that means, yeah, this index I has k number of smaller items on its left. Obviously, everything on the left has a smaller index, and the values are also smaller. Okay, so we just keep track of it. Let's say we have a flag. We have a flag array or something like that, right? So we make this flag like true. Okay, so we keep on doing this, and we keep on filling up this flag. We keep on filling up this flag, right? So every time I just go and do the same thing. Okay, and then once I reach here, like this flag is done, like everything I fill up, then what I do is I just empty the array, just empty it up. I just empty the, sorry, I empty the heap. Okay, and now I keep on reading from the right side, from the end of the array. And again, do the same thing. I read one, add to the heap, and then I reach again to the ith index. And I ask, so by now, say the tip of I is, say, again, is something like is D, right? So D is somewhere here. Anyways, so I ask, and the size of the heap is already K. So I ask, hey, D, are you smaller than X? If D is smaller than X, can we imply the same thing? All Ki items in the max heap are smaller than X. That means, okay, now I know that this portion has K smaller values than X. Next, what I have to check, I have to just check this flag. This flag, what does this flag say? This flag says that X also had K items smaller than X, right? Okay, now I can say that I is K big in index, right? I is K big. So I just count the answer or count this K big number by 1. Let's go and have a dry run. I think that would be really helpful. Let's say, uh, let's not go through everything. Let's say this K value is like 3. Okay, let's not go through everything. Let's just do this. We have started reading from here, and then this is our heap, right? This is our heap. And then we keep on reading this, and we have reached here. So we have started reading, and then by now we have reached here, and this is index I. Now let's see what is in the heap so far. Initially we had put like 4, right? We had put 4, and then we had put 11. 11 was then on the top, right? And then we had put 14. What happened is 14 went into the top, 11 is now inside. Now, by now, the size of the heap is already, say, 3, right? Then we added 18. Okay, so when we actually added 18, you see that 18 already asked this question, hey, 14. So can we say that this one already by when we reached 18 asked compared against 14, and so that 18 is larger than 14. So can we say that 18 has like already 3 values that are smaller than K? So we just set the flag for this as T, right? Okay, these were false because there were not still K values in the heap. Okay, so next we add 18 to the heap, but what happens is we add 18 to the heap, 14 goes down, 18 comes here, but the problem is we have to keep the size of the heap 3. So what we do is we just, to do that, we have to just remove the top of the heap. Whenever the size of the heap becomes more than K, we just remove it, so 14 goes up again. Okay. Now let's skip every other thing. So let's say these things were also set. Now let's think about the reading from the opposite direction. So once we reach like everything is set, then we start reading from the opposite direction. So we start reading from here, right? Okay. And before that, we empty up the heap. We empty up the heap. We are starting reading from this opposite direction. We add 6 to the heap, and then we add 3 to the heap. Now 6 will go up and 3 will be inside. And then we'll add 16, right? 16 to the heap. And 16 will actually go up and 6 will be here. Okay, so this will look like, but by the time we reach I, let's see what happens. Okay, so the flag for I was also set to true, because there were like 3 elements already in the heap that were smaller than 16. Okay, let's see, and we'll keep on reading this. So by now you understand that by the time we will reach here, the ith index, the heap will only have the smallest 3 elements from here, right? Because we are keeping the size of the heap constant to 3. So what are the smallest 3 elements? It will have, it will have 3, it will have 5, and it will have 2, right? So it will have 2, it will have uh, 3, and at the top there'll be 5. Okay, so we have reached this, the ith element. So it will first now check, hey, 16, and you see that 16 is greater than 5. Then we can say, oh, okay, these portion, right? So these portion has 3 elements which are smaller than 16. Yes. And not only that, this flag says that these index I also had, say, k elements, that means 3 elements in the left as well, which were smaller than 16. That means this index is a k-big index. So we just count the number of answers by 1. Okay, so this is the simplest logic. So we keep on doing this for every element. So in total, what operations we are doing? So one time we are just reading this direction, everything we are reading from this direction. So n elements, and each of them we are putting into the heap and then removing from the heap, and the size of the heap is k, right? Always we are keeping it k. So the heap operations are insertion or deletion from the heap, everything is log k. So n log k, that is from this direction when you are reading from the left to right, and from right to left also we are doing it the same things in log k. And in the meantime we are just doing some and also, what is the space complexity? You see the space complexity is like we are keeping just this extra heap. So that is order of k. That is the space complexity. And this is the time complexity. Okay. So now we have a better one. Before we had order of n squared, although there was no space complexity, but if the k is constant, then this space complexity is also constant. Let's go and check the code. Okay, so I already have coded it. You see, we have this heap, a priority queue in Java, right? And this is a max heap, as we said. And because we are having a max heap to just store the smallest element and the highest element at the top, we are just inverting the order. So we are using the parameter. The initial size of the heap we are keeping like number of elements in the input. But actually, we could put just k plus 1, because every time it becomes k plus 1, we just reduce it by 1, right? And we keep it k. So that's fine. But practically, we are keeping the heap all the time, maximum of k plus 1, and then we're reducing it. So you're trying to keep it at length k. Okay, so we could just say k plus 1. One extra element, and then we shred it. And then we change the order, because the default heap is priority queue is a min heap in Java. So we change it to max heap. And then we keep this flag, as you see, the flag to indicate whether there are like k smaller elements on the left of an index, right? And then we fill the flag array with false and answer. This is the answer that will increment. We initialize it with 0. And then from 0 to length of the input, we read one input at a time inside this folder. We read one input at a time. This is the first time reading from left to right. Every time we'll check if the size of the priority queue or the max heap is already k, and the top of the priority queue is already, okay, this would be smaller, right? Already smaller than the current number. Then we set the flag to true. And then we add the current element to the heap, and immediately we check if the size of the heap is greater than k. In that case, we remove the top element from the heap to make sure that the size of the heap never goes, like, comes back to k. Okay, so that's how, using this for loop, we just fill up this flag array, right? Okay, and then we clean up the, like, clear up the heap because we are going to reuse it. Then we start reading again from the right side, and then until the beginning of the heap, and then we check if the size of the priority queue is already is at certain point k. That means there are k elements in the priority queue, and the top of the priority queue is smaller than the current element. Okay, that means that all of the elements in the priority queue are smaller, and also there, the flag is true. That means there are k elements on the left of that element which are also smaller. Then we say, okay, this is k big index, so we increase the answer by 1. And obviously we keep on doing the same thing. We add the current element to the heap and see if at certain point the size of the heap just crosses k. We reduce the top, shed the top element to bring it back to k. And finally, after the second loop, we are done. We have found all the k big indices, we have counted them, and we return the answer. Okay, so if I submit it, oh, okay, so there was one mistake. So it has to be the smaller than the element, right? Yep. So the top of the heap has to be smaller. Yep. Submitted, and you see this is our algorithm, and we discussed also the time complexity of the algorithm, right? Just putting every element into the heap, and sometimes removing it sometimes. Okay, so it's order of n log k, and the and the space complexity is order of k. That's it. Thank you very much for watching. We'll come back with another problem next time.